Okay, guys, so now we're going to start with the properties of the exponential function or the definition of the exponential function. Actually, I'm going to write here the general form of the exponential function. Okay, and here I want to make you remember the linear functions. You know, with linear functions or with quadratic functions, we had a formula, we had a general form that allowed us to represent any any quadratic or linear function that exists. Okay, so you know, like if I say f of x equals mx n times x plus b, that lets me represent each and every linear function in the world. Okay, if I want to do the same thing with exponential functions, I'm going to get something a bit complicated. Okay, I just want you guys to check it out. This is going to be something like this. A times b raised to the power of c times x plus b, and all of this plus e. Okay, this looks a little bit complicated, right? So that's why I'm going to use, instead of using this formula, we're using a simpler formula, and I'm gonna tell you what these numbers will do to our function. So sorry, we're going to use this way simpler general form, which is the one that you can see in your book, and it's not that scary. So this is going to be f of x equals b raised to the power of x. Okay, and this has a condition, which is that it should have, this is with, let's make it right. Okay, where, instead of with, where b is larger than 0, b cannot be negative, b larger than 0, and b different from 1. Okay, so let's do it like this. Okay, so this is a general formula, general form for an exponential function. F of x equals b raised to the power of x, where b is larger than 0 and b is different from 1. Okay, let's find a couple of examples. Couple of examples here. Sorry. A couple of examples here, and this is going to be, okay, insert function. For instance, 2 raised to the power of x. This is one of the simplest exponential functions that you can see, okay? And this b being different from 1 is because if this is 1, this is going to be no longer an exponential function. If I raise 1 to the x power, it's a line, it's a straight line, it's a constant, okay? Because The one, regardless of the value of the exponent, it's going to remain the same value. Okay, so that's why b has to be different from 1. Why does b have to be different from 0? Sorry, larger than 0. Why cannot b be negative? I could show you, but trust me, this makes your life easier. Why? Because this avoids complex numbers to appear here. If this b is negative, if this b could be negative, we would have complex numbers here, and we don't want to have complex numbers here. So just trust me, it's better if this b is positive. Okay, so this is the general form of the exponential equation. F of x equals b, a base b and an exponent x, where the base has to be positive and it has to be different from 1. Okay, so this is an example, 2 raised to the power of x. You will find another common example, which is this. And what's that? Okay, it's a bit weird. E, that's a letter E. Okay, don't be afraid. You just need to know that this is a constant. This is a math constant. You know, if I write pi here, GeoGebra of course gives me the value of pi because it's a math constant. It's very important. It's very important in math. It has many applications, geometry, many things. And it's 3.14. You know that. That's in your head, and it has been for a few years so far, and it didn't harm you in any way. So from now on, you have to add a new piece of information here, and it's that there are several math constants that are very useful and very common, and E is another one of them. Okay, the only thing you need to remember about E, which by the way, one of is called the Euler's number, okay, E, Euler's number. The only thing you need to remember is that it's very, very close to 2.7. That's the only thing you need to remember. It's an irrational number, which is very close to 2.7, actually 2.72, but it's just an irrational number which is close to 2.7. Why is this interesting? You must be thinking right now, like, why do I want to know a new math constant? Okay, those of you who are thinking, oh, mister, I'm studying economy, I don't care about this. Okay, one of the main applications of the number E, the Euler's constant, is in economy, compound interest. It's applied in Bernoulli trials, that's probability, that's statistics. Statistics too. Okay, so yes, the only thing I'm asking you to do is just remember this is a math constant which is close to 2.7. Okay, so in your book, in the exercises, you might find functions like this, e raised to the power of x. Don't worry, just remember this e is almost 2.7. So actually you say it's not that different from 2 raised to the power of x, okay? And this is just one of the most common examples in exponential functions. And later we will use this constant e as well when we are learning about logarithms. But then we'll leave this as another example of an exponential function, e raised to the power of x. Okay, so let's call this types. Okay, situations we usually model with exponential functions. So there are two of them. There are two very, very common situations that we model using exponential functions. And those are exponential growth and exponential decay. When you're solving the exercises from the assignments in this unit, you will see which one is each of them. A situation with an exponential growth is the same as we did with the coronavirus spread. The same thing I talked about before in the previous video when I was talking about the increase in the use of internets worldwide. So it's what you already know. It's just a magnitude that it's growing exponentially. That's an exponential growth. And that happens when when the base, this happens when the base here is larger than 1. Okay? If I have this, let me erase this. When I have 2 raised to the power of x, okay, it's exponential growth. If I write here 10 raised to the power of x, it's exponential growth. If I have, I don't know, 100 raised to the power of x, that's exponential growth. If I have 20,000 raised to the power of x, it's exponential growth. Okay? As long as this number, the base, is larger than 1, this is an exponential growth. Okay? So an example here could be the same f of x equals 2 raised to the power of x. Or this e as well could be an example. But let's leave this one. Okay? I hope that one's clear. It's very easy. That's a typical example, but there's another typical situation we model using exponential functions, and it's the exponential decay. Okay, what does that mean? This is this situation. Instead of growing exponentially, it's decreasing exponentially. The typical example here, and that's the one you can find in the book, in the page 530, it's about chemistry. We have a specific quantity of an element, of a radioactive element, and it starts to disappear with time. So after X minutes, how many grams are there left of this element? Okay, that's a typical example of exponential decay, but it's just the opposite. It's just some magnitude which is decreasing following an exponential curve, on an exponential pattern. And this happens when the base ranges from 0 and 1. So b is larger than 0 and it is smaller than 1, we will see a situation of exponential decay. For example, we have here 1 over 2. We've had 1 over 2 here. Let me make this a little bit bigger. No, that was a bad idea. Okay. So f of x equals 2 raised to the power of x. F of x equals 1 over 2 raised to the power of x. Let's make a couple of examples here, equivalent examples with the other ones. So 1 over 10 raised to the power of x. Okay. Let's do the same thing here. 1 over 100. Sorry. So 1 over 100, all of this raised to the power of x. I'm going to erase this one. Okay, so here I have, let's get rid of this one. Same thing. These are all examples of exponential functions with b between 0 and 1, which represent an exponential decay. Okay, those are the two situations we model using exponential functions. Okay, so now we are going to Sorry, first, before going on, I have to tell you something here. And it's that f of x raised to the power of minus x. Now I am going to make this bigger, indeed. So this is also an exponential, a function that represents an exponential decay. Why? This, now you're seeing this and you say, I don't understand. Like, okay, there's a minus on the x, but what does that mean? What does that make on the function? What does it change in the function? Actually, what I need you guys to notice is that this is the same as this. Okay, you might not remember that straight away, but we learned this the second bimester, I think, when we're learning about exponents. Okay, you remember that really fun exam about exponents? Okay, now it comes back. This is the same. Let's review this a little bit. This is the same as doing this. I'm sure everyone agrees with this. 2 raised to the power of minus x is the same as 2 raised to the power of minus 1 times x. Okay, no problem here. Then, by applying the properties of exponentials, I know this is the same as doing this. This is the same as having this 2 to the power of minus 1 inside of a parenthesis with an exponent x outside. Because if I have this and I want to put all together, these two exponents will multiply each other. So I will get this. Okay, that's why this is equivalent to this, and this is equivalent to this. And once I have this, I have this last step, which is the easiest one. It's that if I have 2 raised to the power of minus 1, this is the same as having 1 over 2. So, because I will have this 2 with a positive 1 as an exponent, but I don't write it, as you know. I don't need to. So this is equivalent to this. What you need to remember when you see this, it's the same as this, and I'm going to prove it for you. If I write here 2 raised to the power of minus x, this graph goes on top of the other. Actually, I'm going to make this more explicit. This is q of x equals 1/2 raised to the power of x, and then I'm doing this one. I'm going to show the value as well, and it appears here it's p of x equals 2 raised to the power of minus x. I can remove one of them. They are the same function. Okay, so from now on, if you see this, don't get scared. It's this. Okay, it means that this 2 is in the denominator. Okay, so before finishing this video, let's talk about the general characteristics of a exponential function. So then now I could call this part properties of the exponential function. Okay, and in order to, sorry, actually here, instead of using these ways of writing them, I'm going to use these ones. I know you guys are hating me for doing this, but I think it's actually better for you. So I'm going to get rid of this, which are easier to see, and I'm going to leave them like this. So let's make all of them visible, and you can see something here. Let's go first with the ones that represent the exponential growth. Okay, something I can see here. This one I don't like that it's a dark color, so let me make it blue, for example. This one is going to be red. Okay, sorry, it's going to be orange because I'm going to use the red later. So you see these functions describe this shape, and they have one characteristic. This they'll go through a point here. Actually, they're going through the same point, but let's not get into that. And what happens here on the left? It's like they are getting very close to the axis, but actually they are not touching it. And I'm going to show it for you. I need to show it to you. So if I write y equals 0, which is the equation for the axis, let me make it visible using a dot line and making it a little bit thicker. Okay, here, if I get close, very close, I can see that actually this function is not touching the axis. It gets really close, but it never touches the axis. And if I go to the left, the same thing happens with the blue function. It gets close, but it never touches it. Look at now the green function, it seems that it's touching, but it's over the axis. But if I get closer and closer and closer and closer, at some point I can realize it's not touching it. And that is what we call an asymptote, asíntota in Castellano. Let me write it down for you. Actually, if I do this, it's faster. Okay, so let's say that one of the characteristics, one of the properties of these exponential functions is that they or it always has an asymptote, una asíntota. Okay, and let me give you a definition for this. Not a very formal definition, but something for you to know what it is. Asymptote is just a line which is, or let's say it's a line which the function approaches but never touches. Okay, asymptote is a line that the function or which the function approaches but never touches. Okay, that's an asymptote. Okay, so properties of the exponential function, it always or it has an asymptote, and actually and here we can say it has only one. Well, as any function, it has only one y-intercept. Of course, any function can only have one y-intercept, because if it has two y-intercepts, it means it's not a function. Okay, but actually, let's see that this one is not crossing the x-axis. This case, in this case, the functions will not have an x-intercept. But I'm not writing this as a rule because that doesn't apply to any exponential function. Okay, only these ones with this basic general form are the ones which have the asymptote at x equals as y at y equals 0, which is the x-axis. So the only two characteristics we can remember is that it has the y-intercept as any other function, and it has an asymptote. Okay, and I'm going to stop this video here, and I will continue in the next one with the different modifications that exponential functions can have.